All right, so here's a review for astronomy, the basics of astronomy, and also some in-depth stuff about planets and the solar system and deep space. Okay, so again, we're going to do the same style of review where the question is posed, the question will pop up, you answer the question the best you can, and then I will be explaining it. So, question one. What is one piece of evidence or proof of the Big Bang? So one piece of evidence or proof of the Big Bang is cosmic background radiation. So the idea is that when all this matter formed, it was so clustered together that light was bouncing around, and then once all this matter ended up separating and cooling enough, the light was emitted, and that is going to be going in all directions from everywhere, from everything, and that is going to be our cosmic background radiation. Proof of the Big Bang. How old is the universe? The universe is, you should have this memorized, 13.8 billion years old. And the proof of that is the cosmic background radiation. What proof do we have that the universe is expanding? So the universe is expanding, and the proof of that is redshift. The idea that the light is being stretched so much to the extent that we can see that these spectral lines are shifted towards the red. So this is an object on the Earth that we measured, and this is an object in outer space shifted. Watch the black lines, they shift towards the red. Proof that the universe is expanding. How does the force of gravity change as two objects become closer to each other? So if you've ever played with magnets, you can experience something similar to this. The closer you get magnets together, the more force they feel between each other. So the closer an object gets, like this object orbiting the sun, it becomes more gravitationally pulled, so it goes faster, and the further it is, the slower it goes. So the fast motion is proof of stronger gravity, and the slower motion far away is proof of less gravity. So the closer we get, the more gravity increases. What process produces the energy within stars? Energy in stars. That process is the combination of lighter elements into heavier elements, also known as fusion or nuclear fusion. I would also accept light elements combining to form heavier elements. What do we observe when viewing galaxies moving away from us? So the reason I ask this question is because it's the same idea as the expanding universe. If the universe is expanding, that means objects or galaxies are moving away from us. So the same answer applies. It's going to be the redshift, also called the Doppler effect, the Doppler radar. But you don't have to know that for this part. We'll learn about the Doppler effect when we talk about weather. For now, redshift, proof that the universe is expanding or that galaxies are getting further from us. What concept about the universe does redshift prove? Again, redshift proves that the universe is expanding. Okay, that's enough redshift stuff. How old is the universe? Hint, it's on page 8 at the bottom left of the reference table. The universe is 4.6 billion years old. The reference table shows that the millions of years ago, so these are millions of years ago, so 1,000 million years is just a billion. And if we go all the way down, we'll see that this is the estimated age of the Earth and the solar system, which is 4,600 or 4,600 million, which is simply 4.6 billion years old. The sun, Earth, and billions of stars are all within the, gotta give me the name, Milky Way galaxy. So I would not just accept galaxy, you gotta say we're in the Milky Way galaxy, gotta be specific. So that's going to be the sun, the Earth, and billions of stars. So I'd also accept the universe, but Milky Way galaxy is the best answer for that because that's probably what the Regents exam is going to be asking you for. The above image shows spectral lines observed in a lab on Earth. Which of the following spectral lines would be observed through a telescope focused on a distant galaxy? A, B, or C? So, these spectral lines, they never smush together or pull apart. They just shift, which is why we call it the redshift. So this next image really helps show that B, option B, is showing us that there is a shift, not a squeeze or a stretch. There is just a shift of light because the universe is expanding and objects are moving away from us. What is a nebula? A nebula is a cloud or a giant cloud of gas and dust, and this is where stars form. It's like the star nursery, and from stars, solar systems form around these stars. What's the definition of luminosity? So luminosity is how bright a star or how bright something is. So the reference table has that in it, and we need to be on page 15 at the top of the reference table for this. Just a hint. Anything that asks you about stars, usually other than nuclear fusion, is going to be in the reference table. What happens to the average main sequence star once it enters the intermediate and late stage of its life? So it first becomes a red giant, and then it runs out of energy and becomes a white dwarf. Here's the proof of that. Here's the main sequence, or the early stage. The intermediate or middle stage is going to be a giant or supergiant. So they'll usually be red giants, right? So these giants are usually red giants. And then once they lose their outer atmosphere, we're left with just the hot core, which is technically a white dwarf. Okay. So that's when a star is dead. It becomes a white dwarf. It's not active anymore. There's no more nuclear fusion. It's just really, really hot because it's the center of a star. So which star, or what star, has a temperature of 8,700 Kelvin and a luminosity of 750,000? So the temperature is 8,700, so each one of these goes up by 1,000 until we reach 10,000, then we go up by 10,000. So 8,700 is right about here, which means it's got to be in somewhere in this area. All right, so somewhere in this area. And the luminosity is 750,000. So that's going to be the net, right where the 8,700 Kelvin crosses the 750,000 luminosity or brightness. The neb. What is the temperature and luminosity of 40 Eridani B? So I need the temperature and the luminosity. The temperature of 40 Eridani B, temperature is 17,000 Kelvin about, and luminosity is really low. If you got less than 1, I'll accept it. So 40 Eridani B. So yeah, it's about, you know what, I gotta take 0.02-ish around there. So if you said 0.03, you're good, but just since there's the 0.1 there, we're between these two, so it's gotta be 0.0 something. How long does it take for the moon to orbit the Earth once? So the main idea here is that the other word for orbit is revolve, and we have information about revolution. So we've got Earth's moon. How long does the Earth's moon take for it to revolve around the Earth? That is 27.3 days. And just a side note, the moon's revolution is equal to the moon's rotation, right? Earth's moon is 27.3 days, and the revolution and rotation are equal. So this means that we always see the same side of the moon, always see the same face of the moon, because the moon's revolution equals the moon's rotation, same amount of time, 27.3 days. Now this next question has to be memorized. How long does it take the moon to cycle from new moon to new moon? They could also ask this to cycle from full moon to full moon. this is going to be 29.5 days. So if they ask you about how long it takes for the moon to cycle, that's memorized. That's 29.5 days. If they ask you how long does it take for the moon to orbit the Earth, or to orbit or revolve around the Earth, that's in the reference table. You don't have to memorize that. You just have to know that you look in the reference table for that. At what position will a lunar eclipse occur or be observed? So we've got all these positions here. So a lunar eclipse means that the moon is being blocked. The only place the moon can be blocked is by the Earth. This is the Earth's shadow on the moon. So if this is the Earth's shadow falling on the moon, position 5, or a full moon, is where we'll have a lunar eclipse. So where will we have a solar eclipse? A solar eclipse is when we'd be observing, I don't see Fred. It's where we'd be observing the sun being blocked by the moon. The only time we can be on the Earth and see the sun being blocked by the moon is when the moon is at position 1, right? It's blocking our view of the sun. Jovian planets. So compared to terrestrial planets, Jovian planets are, so just a reminder here that the Jovian planets start with the J for Jupiter. So these are our Jovian planets. They are giant gas planets that rotate really fast, but they revolve really, really slow, and they are low density because they are gas. So with that information, Jovian planets are huge, because like Jupiter is the biggest planet, and they are less dense because they're made of gas, okay? So remember, these are our Jovian planets, Jupiter, Saturn, Uranus, and Neptune, and terrestrial planets are the first 4, Mercury, Venus, Earth, and Mars. Remember that the sun is a star, and Earth's moon is, you guessed it, a moon. Which planet is the densest planet? So if we're worried about density, boom, there's density. So the most dense planet is 5.5 density. So what's the name of that planet? Earth. We are on the densest planet. The least dense planet is Saturn, right? And Saturn actually has a density less than the density of water. What is the altitude of Polaris in Buffalo? Remember, altitude to Polaris equals your latitude. So the latitude of Buffalo is 43 degrees. So the altitude to Polaris must be similar, right? So here's Buffalo. If I read across, its latitude is about 43 degrees. So that means they have to look 43 degrees up in the sky to see Polaris. And the final question, how much time passes between a high tide and a high tide? So remember, there's 2 high tides a day. So they are 12 hours apart. You could also use this chart. This is about 1 a.m. here, and the next high tide is about 1 or 1:30 p.m. So really it's about 12 hours, 15 minutes between high tides, but for earth science sake, 12 hours. All right.